A scream races forward, then a crystal leaves it behind. A trench drops deeper, then pressure crushes beyond imagination. A dust grain drifts through space, carrying a star's fingerprint. So what wins this comparison? Speed, depth, or distance? Tonight, we are not comparing destinations. We are comparing what matter does inside them. By the end, air will feel slow, the ocean will feel shallow, and space will feel strangely reachable for one reason. Start with the number people think they know. Sound in air moves about meters per second. That sounds fast until lightning exposes the limit. You see the flash first, thunder arrives later. Light outruns sound so completely, the sky demonstrates physics instantly. But speed of sound is not fixed everywhere. It depends on the material carrying the vibration. Temperature matters too. Warmer air lets molecules pass energy faster. Cold air slows the handoff down. Already, the comparison stops behaving. Fast depends on the pathway, not the noise. Now picture a steel rail beside open air. Tap the rail, then listen. The vibration through metal arrives sooner. People noticed that long before modern instruments. In solids, atoms sit packed closer together. A push reaches neighbors faster than in gases. That is why older railroad workers sometimes used tracks. The metal transmitted warning vibrations earlier than air did. The same event produced two travel times. One sound lagged behind its twin. So the first surprise is simple. Your ears do not only hear speed, they hear the medium's architecture. And architecture gets much stranger from here. Shrink the scene to a quartz crystal. Quartz hides in sand, rock, and kitchen counters. Yet perfect quartz became a timing machine. Squeeze quartz and it produces voltage. Apply voltage and it vibrates predictably. That piezoelectric behavior helps clocks stay consistent. A watch looks calm on the outside. Inside, a crystal is pulsing thousands of times each second. Many quartz watches use vibrations per second. That number is not random. It divides neatly by twin, again and again. Electronics love regular divisions, so a common mineral became portable precision. And quartz reveals a deeper rule immediately. Ingredients alone never tell the whole story. Structure decides behavior. The same atoms can become completely different realities. That idea matters for clocks. It matters even more for extremes. Carbon proves that with almost rude simplicity. In graphite, carbon makes soft pencil marks. Layers slide apart easily. In diamond, carbon locks into a rigid 3D network. Same element, different bonding, different result. Graphite feels fragile between your fingers. Diamond is among nature's hardest familiar materials. That structural switch also changes wave speed dramatically. Sound in diamond can approach meters per second. That is roughly times faster than air. A shout in open sky loses instantly. The crystal wins by a ridiculous margin. And diamond hides another talent people rarely expect. It can move heat extremely well. Not because it creates heat, because its lattice passes energy efficiently. So a gemstone can also become a serious engineering material. Beauty stops being the point. Performance takes over. And pressure is about to rewrite everything again. The deepest ocean point is about kilometers down. That feels like the bottom of depth. It is barely the beginning. Earth's radius is about kilometers. The ocean is a thin film on a giant sphere. From orbit, seas look dominant. By planetary scale, they are almost skin. Below them, pressure rises into a totally different world. At the deepest trench, pressure exceeds atmospheres. That means more than times surface air pressure. A paper cup can return crushed flat. A human body cannot visit unaided, so scientists cheat with hardware. They recreate impossible pressure in laboratories. and the tool they use sounds almost too perfect. It uses diamonds. The same crystal that outruns a scream helps imitate Earth's hidden interior. That is where depth stops being geography. It becomes force. Picture two tiny diamonds pressing a speck. That setup is called a diamond anvil. Its sample can be smaller than a grain, yet the pressure can become enormous. Inside that trap, minerals transform, not necessarily into new ingredients, often into new arrangements. Atoms pack tighter, density jumps, wave speeds change. Color can change too. A tabletop device starts imitating unreachable regions underground. Depth becomes something you can manufacture. That changes how we study a planet. No drill has reached the mantle. The deepest borehole went about kilometers. That is impressive for engineering. It is tiny against kilometers of radius. So most of deep Earth was inferred indirectly.
Scientists read earthquake waves instead. The planet shakes, the waves bend, reflect, and speed up. Those patterns expose hidden layers. Earth effectively scans itself during earthquakes, and some of its most revealing clues come from minerals changing phase. Meet stishovite, a high-pressure form of quartz. Ordinary quartz and stishovite share the same chemistry. Their structures do not match. Stishovite packs silicon and oxygen more tightly. It is denser than ordinary quartz. It often forms during violent impacts. Meteor strikes can create it. That means one familiar beach ingredient can become an extreme pressure mineral. Same recipe, different arrangement, different properties. That myth keeps dying here. Material behavior is not about name alone. It is about atomic order. Another mineral system makes that lesson even bigger. Olivine, common in the mantle, does not stay olivine forever. As pressure rises, it transforms. First comes wadsleyite, then ringwoodite. Go deeper, and denser structures appear again. These are not cosmetic changes. They help control seismic wave speeds. So when earthquake waves suddenly shift behavior, scientists see boundaries, not empty gaps. Not giant caverns, behavioral borders. The planet is layered by physics. Ringwoodite delivered one of geology's best surprises. It can store water in its crystal structure. Not lakes, not sloshing underground seas. Water bound as hydroxyl inside the mineral. That distinction matters enormously. The mantle transition zone spans roughly 2 kilometers depth. That slice sounds narrow by planetary standards. It is colossal by human standards. If minerals there hold even small fractions of water, totals become huge. So surface oceans may not tell Earth's full water story. Blue from space does not mean complete. Some water may be hidden chemically, not visibly. That reverses the usual mental image. We imagine the deep Earth as dry rock. Mineral physics says parts may be surprisingly hydrated. And pressure keeps creating new identities lower down. Farther toward the core, iron-rich conditions dominate. Temperatures climb to thousands of degrees. Wave behavior changes again. Scientists even map liquid and solid regions by sound. Earth's outer core is liquid. The inner core is solid. A planet can have an iron heart with 2 different states. And suddenly, the deepest ocean looks almost delicate. Now jump from Earth's interior to desert dust. A dark stone lands. Inside, some grains are older than our sun. That sounds impossible until isotopes enter the story. Certain meteorites contain presolar grains. These tiny particles formed around ancient stars. Later, they survived stellar explosions and interstellar travel. Then they joined the cloud that formed our solar system. Scientists detect them using unusual isotopic ratios. Their atomic fingerprints do not match normal solar system material. This is not poetic stardust language. It is laboratory evidence. Distance becomes age you can hold in tweezers.
and some of those grains are microscopic diamonds. Others are silicon carbide or graphite. A speck smaller than dust can outage Earth itself. Scale breaks your intuition again. Huge distance hides inside tiny matter. And once space enters the comparison, survival becomes the next question. Space is not just far. Space is hostile. Vacuum removes air and convection. Radiation damages materials slowly and relentlessly. Temperatures swing brutally between sunlight and shadow. A spacecraft cannot stop for repairs. Every component must survive on purpose. That is why stubborn materials matter. Natural moissanite, silicon carbide, is rare on Earth's surface. In engineered form, silicon carbide is valuable in electronics. It handles heat and demanding conditions well. What looks like a jewelry competitor becomes advanced hardware. Again, context changes value. A material praised for sparkle may matter more for endurance. And carbon keeps returning with new costumes. Graphene is one atomic layer of carbon. One layer. That is the whole sheet. Yet it is remarkably strong for its weight. It also conducts heat and electricity very well. Graphite, diamond, graphene, nanotubes. Same element. Wildly different behavior. Matter is ingredients plus arrangement plus scale. Remove any one of those and you miss the story. Some crystals do not just carry force, they manipulate light itself. Look through clear calcite and one line can appear doubled. That effect is double refraction. Light entering the crystal splits into different paths. A simple mineral can duplicate an image. It feels almost fake the first time. It is actually geometry controlling information. Ice can do something similar on grander scales. High in cold clouds, flat ice crystals bend sunlight. That helps create halos around the sun or moon. A sky ring can form because tiny crystals orient just right. The atmosphere becomes optics. The same planet that hides water inside minerals also projects giant light tricks overhead. And light is only one kind of redirection. Magnets reveal another invisible empire. Neodymium helps make very strong permanent magnets. Those magnets power motors, speakers, and compact machines. The real surprise is not merely strength, it is strength in small size. A smaller motor can do serious work. That helps modern devices shrink without becoming weak. Invisible mineral choices reshape visible technology. Even gold changes personality under extreme conditions. On Earth, gold suggests jewelry and vaults. In space, very thin gold coatings can reflect infrared radiation well. That helps protect equipment and visors from harsh thermal environments. Not thick bars, microscopic layers. A luxury metal becomes a survival film. That reversal says everything about material science. The best substance is rarely best in general. It is best for one punishing task. Titanium tells the same story differently. It combines low density, strength, and corrosion resistance. That makes it valuable in aircraft and spacecraft. It also appears in medical implants. Human bodies tolerate it surprisingly well. Yet titanium ore looks ordinary before processing. A dull mineral source can become elite engineering. Corundum adds another twist. Gem-quality corundum becomes ruby or sapphire. Industrial corundum becomes an abrasive. Same mineral family. Beauty and grinding power side by side. And hardness turns into a useful ranking here. On the common hardness scale, diamond ranks 7. Corundum ranks 7. That gap matters. Corundum can scratch many other materials easily. Sapphire windows resist scratching far better than ordinary glass. Ruby and sapphire differ mainly by trace impurities. Tiny chemical additions create major color differences. A little chromium can help make ruby red. A little iron and titanium can influence sapphire shades. So color itself can depend on minute contamination. perfection is not always purity. Sometimes the impurity is the feature. That also happens in everyday chemistry. Table salt and diamond seem unrelated, yet both can grow as crystals. Snowflakes, quartz, sugar, and metals can all form ordered structures. Order repeats from kitchen scale to planetary scale. Once atoms choose a pattern, behavior follows that pattern relentlessly. That is why one crystal keeps time, another bends light, another survives the deep mantle, another carries clues from dead stars. The hidden world is not elsewhere, it is inside arrangement. So, which wins our comparison? A scream moves fast for a body. A diamond carries vibrations much faster. The ocean looks impossibly deep from a ship. Earth's interior makes that depth feel like a surface wrinkle. Space seems empty and unreachable. A meteorite can deliver presolar material into your hand. Speed loses its pride. Depth loses its drama. Distance loses its remoteness. Matter keeps changing the score.